Hello everyone, welcome to the week 7 project presentation that is on deformation of areas and volume. A quick overview of what I'll be discussing in this presentation. First, I'll be defining my body and parameterize it. Then I'll define surfaces on that body and I'll define volume for that body. Then I'll define a deformation map, and using that deformation map, I'll compute its deformation gradient. And lastly, I'll compute areas of the surfaces and volume of the body using MATLAB, and I'll verify for one surface and one body volume using hand calculations. So the body I've chosen is an I section, and the parameterization is here. This is for the bottom flange, that is this one. The same thing can be done for the web and the top flange. And here I have defined some surfaces too to compute areas and volumes. Then I have defined tangent vectors to this body. This I've defined tangent vectors to the body, and that can be done just by differentiating its body parameterization with respect to the parameters. And here is the deformation map. The deformation map I've chosen is can be imagined as a vector field that would be giving a displacement. Let me explain it like this way. Let's think of a unit point load acting on this end and this end to be fixed. So the deformation it would present in the beam, it would cause in the beam is given by this. And just making like adding these terms with x, y and z will give us the deformation map. Taking its partial differentiation with respect to the parameters will give us its corresponding deformation gradient, which is also known as tensor field. Here is the code I have done in the MATLAB to obtain some results, which I'll show in the following slides. Here is the deformation map, and here is the corresponding deformation gradient. Now, coding that, I get the deformed and undeformed lengths, deformed and undeformed areas, and deformed and undeformed volumes of the body. And as you can see, the deformed and undeformed areas and lengths are mostly same for some surfaces and curves, because the deformation gradient is constant in y and z, and it's only changing along x, and that too with respect to height, that is z. So this curve, which is this one, has its height and areas changed, and this surface, that is the curve length is changing from 12 to this, and the corresponding surface, that is this surface, its value is changing from 60 to 8640. And the values I'm getting so high is because the deformation gradient is so much that it's scaling it very to a very large amount. Now let's compute the area of the one of the surface. So parameterization of the undeformed surface is this, and its corresponding parameterization of the deformed surface can be found out using the deformation map. The undeformed area is 60. That can be just calculated using length and breadth formula, L into B, and that would be the undeformed area. And to compute the deformed area, I'll take use of the area Jacobian, which is nothing but differentiation of x with respect to t, and the differentiation of this with respect to both the parameters and the cross product. So using that, we get an deformed area as 8640.55 using hand calculations, and the same is obtained using MATLAB too. Now I'll do the same thing for volume. So that can be done using the volume Jacobian of the deformed body, and that is nothing but cross products dot with the other parameters. The cross products are nothing but differentiation of these parameters with respect to one of the parameters, and taking dot with the third one. And from here, unfortunately, I got a gradient that would lead to 1, which I didn't knew when I chose the parameters. So my deformed and undeformed values are not changing. Basically, they are same. Now I'll show you my code if it's running. Here is the deformation, and here is the command window. And here from where we can see that the deformed and the undeformed volumes and areas are as shown that was in the code in the presentation.